Welcome to Math Essential Coordinate System. In this video, we'll discuss about derivative of unit vectors. First, for the Cartesian coordinates, whatever the unit vector you are differentiating, and whether you are differentiating in terms of x, y, z, you will always have a zero because these ones are not changing; they are just basic coordinate system, and the dimensions are totally independent from each other. Now we move to the cylindrical coordinate system rho, phi, and z. And let's have a small recap. We have derived in a previous slide that rho, phi, and k are related to ij and k using these equations. And in order to calculate the derivative, simply what you are applying is d by d rho, d by d phi, and d by dz on this unit vector relationship. First, for the rho, what you can notice here in the right hand side, there is no relation with rho, so always you will get 0. Likewise with z, you will get the same. There is no relation, there is no z factor here. You will always get also 0 here. But in terms of phi, you can see here cosine phi and sin phi appearing in the terms of rho and phi. In the term of k, you cannot find anything, so you will get 0 also. So here, this is just the result that partial rho by partial phi will result in the phi unit vector, and the derivative of the phi unit vector will result in minus rho. How this comes? Simply let's apply the derivative here. So we have here rho equal to cosine phi in the I direction plus sine phi in the z direction. If you take partial rho by partial phi, this will equal to sine phi. Of course, you will get a negative here. This will not change here. Plus cosine phi in the j direction. And you just compare this result here with the phi. You will find they are equal to each other, so you will get phi. Likewise, if we bring here the phi unit vector, which was equal to sine phi plus in the I direction plus cosine phi in the j direction, if you apply the derivative partial phi by partial phi unit vector by partial phi will result in minus cosine phi plus, then you will get minus phi in the j direction. And if you compare this one with this one, you will find it is equal but with minus sign. So we have proved these two relations. Now we are with the spherical coordinates r, theta, and phi, and we have here a recap again, the relation between r, theta, phi, and ijk, which can help us to find the derivative. If we look carefully, we don't have any dependency here in r, so if we differentiate either of these r, theta, phi with respect to r, we will always get a 0. If we move to the theta differentiation, so we differentiate r with respect to theta, we'll get this result. So let's do it together. I'll do partial r, partial theta equal to, here we have sine theta, so this will bring you with cosine theta. Cosine phi is just constant with respect to theta. I will come here plus another sine theta, it will bring you also a cosine theta. Sine phi just a constant j. Cosine will be minus sine theta in the k direction. And if you compare carefully this term here with this term, they will be equal. So this will bring you with theta. So this one is now proved. Let's move to the second one. I want to find partial theta by partial theta equal to, we have here a cosine, it will turn to minus sine theta. Cosine phi is just a constant in the I direction, minus again cosine theta. This will turn to minus sine theta. Cosine phi is again constant in the j direction, and we have a minus sine theta, it will be again minus cosine theta in the k direction. And if you compare this one with the one here, you will find it's the same but with minus sign. So this one is also proved. Now final one is phi component. If we differentiate with respect to theta, we don't have any dependency here in theta, so we'll get a 0. Move to the phi differentiation. So first with r, we have something, so it will have a result. So partial r by partial phi will equal to, here we have sine theta, this is a constant, cosine phi, it will bring minus here, minus sine phi in the I direction. Let this just keep positive for now. We have sine theta, this is just constant. Sine phi will bring you with cosine phi in the j direction, and finally here we have no dependency in phi, so this will be 0. And now if you compare what you have here with the phi, you will find it is the same but multiplied with sine theta. So you can simplify this one by sine theta multiplied by the phi component, which you can see here. Likewise, let's do for the unit vector theta. So here it's theta, so let's differentiate partial theta by partial phi equal to what? We have here cosine, it will come as is. We have here cosine phi will give you with minus sine phi in the I direction. Again, we have here cosine theta, this just cosine theta. We have sine phi, this just bring you with cosine phi, and this one is j direction, and again we have here no dependency in phi, so you will get a 0. And if you simplify this one, you will just find this equal to cosine theta multiplied but what you can find here, which is phi, so this one is also proved. The final one with us is the differentiation of the unit vector phi with respect to phi. So let's do here in this point. So we have phi by partial phi equal to, we have minus, this sign will be cosine phi in the I direction. We have another minus, which is a result from the differentiation of cosine, so you will get minus sine phi in the j direction, and this one is actually just minus rho, and we can recall together that rho, this one, let's move here, this rho is just equal to sine theta in the r direction plus cosine theta in the theta direction. And since we have a minus sign here, so you'll find the result will be this one here. Now we are with the takeaways. In the Cartesian coordinate system, we cannot find any derivative of the unit vectors, but if you move to cylindrical and spherical coordinates, because we have a rotation and angles, we find that we have some derivative. I mean, not every derivative is equal to 0. It's actually very important in quantities like divergence and curve, and in general in vector calculus. Thank you.